Thank you all for being here. Thanks to the organizers for inviting me and for putting together this absolutely amazing workshop. I've been really enjoying it. Okay, so I'll be telling you a little bit about the work we've been doing on quantum algorithms for our specific purpose. So I come at this not from a mathematics perspective, but from as a physicist. And so while we do some bit of math, a lot of it is a little bit more application focused. So this might be a more application focused talk than you've seen all week. And as an added bonus, it has actual quantum computer data for the first time this week. So that'll be good. All right. I should thank my group. A lot of the work that I'll be presenting today has been done together with Efekan Kökçü and Hebel Habib. And there's some other folks, some of whom are here, who we've gotten some work with also. Okay. So to motivate all of this, I should tell you about two phase transitions that you might see in physics textbooks or in your physics courses. There are two different types of magnets that tend to be studied. One is called Ising or Ising, depending on which side of the ocean you're from, and the other one is Heisenberg. These are supposed to be representative of some real materials. Mostly they're not, but you can get kind of close. This is rubidium cobalt fluoride that is kind of Ising-ish, and this is rubidium manganese fluoride, which is kind of Heisenberg-ish. Probably more familiar to you are their Hamiltonians. The key distinction between these being that these are Z couplings only, and these are X and Y and Z. Okay. So now if you come from, say, quantum machine learning or variational quantum algorithms, one of your tasks might be to prepare the ground state for these models. So you pick your favorite thing. You maybe do some kind of classical optimization algorithm, and then what you find for Ising, you might find these things, ferromagnet or antiferromagnet. And then you try and do the same thing for Heisenberg. You find it's much harder. You have to work a lot harder. You have to have deeper circuits. And when you get it all done, you find sort of the same things. So what gives, right? Like, why are these, these are supposed to be very different, yet I end up with the same ground states, right? So they're supposed to be different materials. So something is weird. So how do you tell the difference? Well, this was actually a question that Andras asked yesterday. It was already on my slides before that. And the question is, what do you do with the quantum state once you've prepared one? And the answer is what you do is you measure its excitations. Why do you want to do this? Well, among other things, your colleagues that are physicists and chemists at various labs, beamlines, whatever, in this case Berkeley and Oak Ridge, do a whole host of experiments. Yes, on interesting quantum materials, whether they're chemistry, whether they're physics, right? They do these experiments, and they go by various very fancy names. We get longer and longer acronyms every year, but they all measure some type of excitation out of your material. Almost never do they measure just a ground state property. Right? So these are the sorts of things that are helpful to do once you have a ground state. Okay. Just to give you some examples, here is some chemical molecule. I don't know its name because I'm not a chemist, right? But what you can do is you can measure absorption, you can see fluorescence, phosphorescence, these various other things. And by doing so, you can learn about the dynamics of this molecule, and that's what our experimental colleagues do. This is an example of molybdenum disulfide. It's been very interesting lately from the physics side, and if you measure its optical properties and you know what these various bumps and peaks mean, you can learn a lot from this. So one of the things that we could do with a quantum state, which we have these, is to try and get at these properties a bit so that we can then make contact with what our experimental colleagues are doing and together try and understand the interesting physics of some molecule or molybdenum sulfide. Okay, back to my two models.
Lex,
yes, please.
Can you say a little bit more about what it means to measure excitation? Like, what's the kind of data that you are wanting?
You mean from their perspective or from ours?
Yeah, I don't know.
Okay, so.
Just looking for something to.
Oh, great. So in this case, right, so this is a good example. These are near IR to UV vis wavelengths. So what they do is they take that piece of material and they shine different color light on it, and they see how much of that color light gets reflected or absorbed or scattered or any of the millions of experiments they could do. For our purposes, I will answer that question in a couple of slides, if that's OK. Good. More questions?
It's something more than just learning the low energy spectrum.
Is it something? In essence, that's what it is, kind of, but a bit more than that, because the low energy spectrum measured by one experiment is different than measured by another experiment. They have access to different things depending on what kind of experiment you do, and I'll say a little bit more about that. Actually, this is a good place to talk about that. This measures the single particle spectra of electrons. So I pull an electron out, then I measure its energy. This thing, among other things, can measure structure. It can measure spin structure, so spin excitations. Right? All of these things are different excitations that you can make in your ground state that tell you something about the physics. OK.
But just to be clear,
Yeah.
They have to do something after they have the ground state.
Yes.
I mean, either bombard it with drill a hole or whatever.
Yes.
So something physical has to happen, right?
Yes. I mean, the nice thing about doing experiments is that the ground state is given to you, yes? And here's your material. You don't have to make it. Yes.
Got it.
Yeah. OK. Oh, and this is also true. Like if if your ground state that you're making corresponds to some differential equation that you might solve, yes? Like, OK, that's not, say, it is still interesting to look at excitations, response functions of a liquid, or whatever, or a gas. OK. Thank you for the questions. OK, so back to these two. The excitations for these two are different. The Ising model really only has one type of excitation. I can flip one of its spins, and this is what it can do. This is the lowest energy excitation that I can make. For Heisenberg, you could also do that, but there's a lower energy one, because what you have in Heisenberg is you don't just have z degrees of freedom, but you have x and y and z. And you can make these small angle rotations away from strictly vertical, and that is the lowest energy excitation that you can make. OK. Good. So from a theory side, we encode these in correlation functions, right? This is my experimental side. Really what they're doing is this. You have some bit of material, whatever it is, and your correlation function, which then encodes all these different experiments, asks the following question. Given that I have some observable that I saw here, what's the amplitude for some other observable there? All of my two-point experiments I can encode in this way. Very good. So you open your many-body theory textbook or one of Rolando's papers, and what you find is these sorts of things. This is how you measure them. Step one, you prepare some state of interest. We've heard a lot of talks about that this week. Step two is you apply whatever the excitation is that corresponds to your experiment. Then you time evolve. We have heard a bunch of talks about this also. You apply your second excitation, and then this is what you measure. You have to do some interference with the ground state for bookkeeping, but that's effectively it. OK. Now, if you go to this paper, for example, you find circuits that look like this, where each one of these pieces is present in reverse order. So you have some, these are my system qubits. I have some unitary that prepares my states. I have some unitary that applies an excitation, time evolves, or unexcites. These two are controlled, and this is essentially a fancy version of a Hadamard test, right? This is effectively what you're doing. OK, good. So you can run this. I ran this back in 2019 for when I was first learning anything about quantum computing in the first place. This is for a four-spin, four-site Heisenberg model. There are three different excitations that I can measure, or correlation functions. If I have four spins, then I can measure the on-site one. I can measure the nearest neighbor, the next nearest neighbor, and I could do one more, but it's periodic, so it's the same thing. So there's only three. The lines are what you're supposed to get. This is a kind of a simple model, so there's really only 2 or 3 frequencies in it, so that's what you see. And the dots are what we got from the quantum computer. Not great. Yes? If you're looking for any kind of metric like fidelity, you would say, man, this is forget it. Like, I'm going to go do something else, which is what I almost did. But so I looked at this and was like, well, okay, I do look like I have some oscillations in this. Yeah, there's some pattern. It's not completely and utterly noisy. So you do a Fourier transform, you do a bit of error mitigation, and here's what you find. You do find peaks at the frequencies you expect. For this model, those are 0, 4, and 8. So you get precisely those frequencies. That's good. What you're supposed to have is, we've also Fourier transformed to momentum space. You're supposed to have the red line. That's where the frequencies are supposed to live. So you do find the largest signal where they're supposed to be, but you do see some leakage between channels. But not bad, right? Given this horrible data, like it's kind of okay. All right. So this was from 2019 from a machine that no longer exists, from one of the IBM machines. Any questions? Okay.
These aren't like off by a phase, and that's why the spectra.
Good. They are exactly off by a phase. There are hardware reasons why they are off by a phase. Even after correcting the phase, that doesn't help the noise as much.
How do you correct the phase?
How do I correct the phase? I know analytically what the first number is supposed to be. It is 1. So I take the whole thing and multiply it by all of the data, and multiply it by the complex number that I know is supposed to be 1. It's like the dumbest thing you could possibly do. But we know this one from some rules. We know exactly what that's supposed to be.
And the rest of the error mitigation, did you assume some sort of error model?
No, this was way before any of these things existed, right? The best you could get at this time was like readout error correction. And that's really it.
So how large is the system?
4 qubits. 5, sorry. 4 for my system, 1 for the Ancilla. Okay, good. Great. So the reason I started with this is a nice example of sort of how I think about things. This is one of the other things that was talked about yesterday, is that we should start thinking about sort of start to end quantum simulation. Prepare a state, do something with it, measure it, get some properties out that you might care about. All right, so these are the sorts of things that are involved in that from this perspective. So my group works on this a little bit. We've done some work on state preparation. We've done a bunch of work on time evolution. Yes?
Is it obvious why you don't need the control on the unravel?
Because, is it obvious to see from here? You're looking for, I don't have a 3-second answer for you. I can write it down given 2 minutes on the board. But effectively, the thing you want to apply this operator and then time evolve this state, and you're looking for the overlap of this one with that one.
And how do you need to control?
Yeah, no, there's bits where you can cancel out some of the Hadamard's if there's stuff that's in common. This is what I was asking about earlier also. I can tell you a little bit later. It's like a minor technical detail. Good, okay. So we've done some work on dynamical response functions, both in closed and open quantum systems. We've done some dynamical mean field theory, which is a physicsy thing. And more recently also, and we saw some things from that earlier this week also, is that some of the classical post-processing techniques can be really powerful for getting some things out that you otherwise would not be able to. Good. So what I'll be telling you about today, depending on how many questions and time, is I'll tell you about a new way of computing correlation functions, response functions, that doesn't require this structure, but is something new. So this is a new algorithm for doing precisely that. And then if I have time, I'll tell you about some of the Lie algebra work that we've been doing. Okay. Good. So response functions. This is now from some time ago, and of course, literature doesn't stand still. There's been a good number of other approaches, some by some folks that are in the audience that I learned about last week. But so there's a variety of approaches that rely on variants of the Hadamard test for open quantum systems. These two are SVT and the Lanczos expansion. This one is more on the hardware side, and we'll be talking a little bit more about that one, or about how this one works. Most of them measure commutators. I'll tell you why that's important in a minute. Okay, so let's take a step back and think about what experiments do. So here's a experimental facility. This is the advanced light source at Berkeley Lab. If you haven't seen it, go see it. It's very cool. It's a light source that was built like 50 years ago. So there's aluminum foil all over the place. It looks like a mad scientist lab. It's amazing. This is a piece of barium iron arsenide. This is a superconductor. And how do you do these experiments? Well, you take your material, you shine light on it, and then you measure some things that come out. Okay. So that's what that looks like schematically. I take my material, I hit it with something, it makes changes happen in the material, and then you measure it sometime later. That's what they do. Our proposal for a quantum algorithm that computes correlation functions, response functions, is to precisely do that. You start with some state. You make an excitation, so your exciting field, whatever it happens to be, goes into the Hamiltonian. You evolve it with whatever the system Hamiltonian is, and then you measure at the end. This works within something called linear response, so we call it a linear response framework. And the idea is just to make the whole excitation, the whole process of measurement, part of the simulation rather than something that you bolt on after the fact. And then once you have your data, you can then post-process to get response functions out. I'll tell you a bit more about exactly how we get there in a minute. This is the sort of data that you can now get out. These are now, to a physicist's eye, pretty decent spectra from a quantum computer. This is now this year for 8 sites. Here's why I might want to do this. When you do the Hadamard test, you need to apply a controlled operator. Must be unitary, right? Because that's what it has to be, unless you want to do encodings and these kinds of things. That is not a restriction here. You can use any operator you want without needing any block encoding of any of the sort. Don't need any extra ancillas. Don't need controlled operations. You can measure many correlation functions at the same time. I could, for example, apply a driving field on the first qubit, measure all of them, and then I can at the same time get the response function for on-site, nearest neighbor, next nearest neighbor, all of these things all come at the same time. I have to do less post-processing, so less noise. And what's particularly nice, and I'll tell you a little bit more about that later, is that we can be frequency and momentum selective. By designing your operator B that you're hitting with, or that you're driving with, if you are interested in a particular frequency range, or if you're interested in a particular momentum, or anything that you want to focus on, you can measure just that, rather than having to disentangle it from everything the system gives back to you. So you can be selective about what you're measuring, and that makes it a lot more error resistant. And I'll show you that too. Okay, questions?
Well, then I have one.
Please.
Have you stumbled over out of order correlation?
It doesn't work for these. It doesn't work for OTOX. We've tried. Or at least rephrased. We haven't found a way to do that yet.
Thanks.
Yep. Good question.
What are examples of initial states that you might care about?
Anything you guys are preparing. So just the system of fermions, Hubbard models, molecules.
I guess I mean, like, are you more interested in the ground state or something else?
Okay, so as a physicist, what I care about here are low energy states or thermal states. But this works for anything you would like. If you are interested in some other one, that's fine. Okay, so the way this works is actually relatively straightforward. And given that this is somewhat of a math conference, I figured I would bother to show you the point. Really, this is something that you can find in most many-body theory textbooks. And it goes like this. We know what our time evolution operator interaction picture looks like. Formally, we can solve it by time-ordered integration, or if v is small, then I can approximate this and just sort of take the first-order term. Now, if I apply this to my wave function, I get my initial wave function back plus a bit that goes proportional to my small v. So now, within this state, I pick some operator that I would like to measure. Okay, well, you can probably sort of see where this goes, right? You take this state, you put it there, you put its conjugate there, and what you get to linear order is the thing in the unperturbed state plus a commutator of the operator that you were after. And if you put the time dependence outside, then the change in A due to my B field looks like this. This is now a commutator between A and B. And this thing is precisely what we call a retarded correlation function and exactly what you would measure in basically any kind of an experiment. Pick your favorite many-body theory textbook. This will be in it, I guarantee you. Usually goes under the heading of linear response. OK. I have this slide twice for some reason. So I'll show you how this works on kind of a toy model. So suppose I have just a single qubit, a single spin. There's its Hamiltonian, sigma z. And I'm going to drive with sigma x and measure sigma x. Here's my driving field. And I'm just going to kick it, right? This is like a bell. I'm going to ring it and see what frequencies I get. Well, this thing only has one frequency in it. So there it is. The harder I hit, the larger of a signal I get. And part of the idea of this being linear response is then what you're supposed to do is you're supposed to look for the regime where your signal is proportional to eta. And that's how you know you're in a linear response regime. So this is really as simple as ringing a bell or a tuning fork or whatever it is you want. Now we can do something a bit more interesting. Instead of doing just a sharp pulse, I can give it some frequency structure. Yes, I can apply this field together with some oscillations at particular frequencies. And now we get something a bit more interesting. I get a very large response when I drive at 2, a little bit less at 2 3/4, and even less at 1. And this is really natural, right? This is just resonance. That's all it is. Right? This is the frequency content of my pulses. That's the place where my system likes to respond at 2. So I've got a huge overlap for orange, less for green, a little bit less for blue. But in this way, you can be frequency selective. You can pick what ranges of frequencies I care about. OK. What else can I do? So this is what this method gives you. That's a commutator, so it comes with a minus sign in between. I might also want to have an anti-commutator. Why? Well, just now in the talk before us, there was a bunch of discussion about fermion signs and these kinds of things. This is precisely why I want an anti-commutator, because all of the sort of fermionic correlation functions that I might want to measure all involve anti-commutators. And one of the really big experiments in condensed matter physics is this thing called photoemission spectroscopy that measures electron spectra. So being able to do anti-commutators is also important. All right. So there's two options for doing this. One, and they're essentially equivalent, but they make use of the quantum computer in different ways. One, you can use some auxiliary operator, or two, you can do some clever pulse selection. It's sort of straightforward. You find some operator P that anti-commutes with whatever B is, whatever B you're trying to measure. It also has to be stable under the Hamiltonian, and it has to be, and the initial state has to be an eigenstate. If that's the case, then you can carry through a couple lines of algebra and show that this thing turns into that. So really, all you have to do is modify what operator you're measuring, and you're golden. That's all you have to do. Now, yes, and as it turns out, parity is really good. So this seems very restrictive, but if all you have to do is measure parity times A, and you're pretty much good. Second option is to use pulse selection. And this works for Hamiltonians that conserve particle number, which are most of them. So what I'm going to do is I'm going to mark how many particles are in my state at any given point. So I start with n particles in the ground state. And now for excitation, what I'll do is I'll apply one of these. This is a Hermitian operator. It's not a problem. So now my system is in a superposition of n plus 1, and n minus 1. That remains true at the end. Right? This conserves particle number. And so now simply by post-selecting cleverly on n plus 1, and n minus 1, I can get the various Green's functions that I care about. So this one doesn't require the same symmetry operator, but it does require your Hamiltonian to conserve particle number. Otherwise, they're equivalent, except that this one involves some post-selection, so your number of shots might be a little bit less. On the left, if it conserves particle number, this will also work. And so both of these work for particle number Hamiltonians that conserve particle number. Or sorry,
Particle number doesn't have to be the PT.
parity does.
Yeah. Particle.
No, fine, but if this is actually less strong than particle number conservation. It's up to mod 2.
Because each is Z,
This thing counts if you have an even or odd number of particles. Yes, that's all it does. Okay. So, actually, any questions? I moved on too quick.
Yeah, actually, maybe.
Yeah.
Sorry, I think I just didn't follow. What's up with this? What's up with this peak?
Okay. What we would like is we would like an anti-commutator. The method, as I showed you from the many-body theory textbook, gives you a commutator. So you have to find some way to turn the minus sign that you get in here into a plus sign. And the easy way to do that is by finding an operator that has this property. Yes? And then in order to shift it from B over to A, you require these other things a little. Okay.
And then your example is parity in the case that, what's the B that you're thinking?
Good.
Where B works?
Creation annihilation operators. So parity anti-commutes with creation annihilation operators. Because really, that's why I want anti-commutators, because those are the things I want to measure. Yeah?
I thought you said that B and A have to be Hermitian at some point.
They don't have to be.
Well, okay.
Sorry, Hermitian, yes. But they don't have to be unitary.
And creation annihilation operators, they're not Hermitian?
They're not, but C plus C dagger is. This is Hermitian.
Okay, so B is always that, okay.
Okay. So how does this work? Well, so here's a test case. So this is some physics model. It's called Sushi-Verheegen model. It's nominally for polyacetylene, but you can kind of think of it as just a chain of free fermions where I can hop more strongly and less strongly between alternating bonds. You pick this one because it's a nice toy model. It is non-interacting, but the method works just fine for interacting also. It is a periodic system, so the eigenstates live in momentum. If my delta, which is the difference between hopping left and right, is 0, I have a normal cosine band structure. If delta is finite, then I have a gap that opens up at the Fermi level. And so these are the sorts of frequencies that I expect to see coming out of my non-interacting system. Okay, good. So now we apply this technique, and now we go, ideally, to measure this. Except here is where we can make use of the freedom of the B operator that we can choose. My eigenstates are in momentum. If I were to make an excitation in real space, I would get all of these frequencies all at the same time, which is fine. I have to disentangle them. You can do that. But if I could drive at a particular momentum, then I would only get one frequency, or possibly two. And this is a better option because we're going to look at noisy data. And it's much nicer to just have one thing to look for rather than 20. So instead, we create a momentum eigenstate. This is what we use for the B operator. And we pick different Ks and then go and calculate this. So this was run on one of the IBM quantum computers earlier this year. And there's the data. Still not great, right? Like I should still be looking at a single frequency, and this is not that. But really all I have to do is just Fourier transform. For delta equals 0, I get, in this case I have two copies because I have positive and negative frequencies, but I get one peak at each frequency that I expect. This one is also nice and clean. This is really doing nothing other than Fourier transforming this data. Right? So this is really clean data from today's hardware. And then there's this one. I think the hardware just had a bad hair day. I don't know. We ran it a couple different times. Sometimes it worked, sometimes it didn't. Turning these into nice, pretty false color plots, these are the sorts of things that you see. These are half of my band structure, and they nicely match the frequencies that I expect. And so this works pretty well.
You have a finite key data. When you say Fourier, just to get Fourier on the finite.
Really, really great question. Good. So this is finite data.
Yeah.
So in this case, what I'm plotting is I've taken just this data, I've Fourier transformed it, and I'm plotting the power spectrum, just to tell you what frequencies are in it.
But isn't Fourier with respect to space?
No, because I've driven at different momenta.
Okay.
Yes? So I specifically, by picking K,
You select the momentum.
I've selected the momentum that I want. And that's one of the things that you can do with this. You don't have to take all of your different R datas and then Fourier transform those.
Do you think there's room for better way to do the signal processing?
Yes, I will show you in a minute. Did you have a question?
What do you mean by compressed circuit?
Good. So this is a free fermionic model. And for free fermionic model, they are fast forwardable. So this is a circuit that if you adjust the parameters, and I have a little bit more about that later in the talk, you can adjust these parameters for any time that you like. The circuit structure always stays the same. But this is because this is a fast forwardable model. This is why we chose this, because if I tried to run 8-site Hubbard model evolution on a quantum computer, that's not going to do anything.
So the fact that it's free fermion, does that also imply that these like calculating Green's function is efficient classically?
Yes. Yeah. No, this is not a model that's hard. Yeah. Okay, I could do this on pen and paper. Yeah. This is more to demonstrate that it works and that you can actually execute this on hardware. But yes. Okay, good. So that's this part of the talk. Ancilla-free, momentum, frequency selective, these sorts of things. Okay, so any questions on this bit? Okay. So Lynn, you asked about this, thank you. By doing some post-processing, we can actually do better. So here again, I show you the raw data. And this is now not the power spectrum, but the imaginary part of the Fourier transform. It doesn't look nearly as nice. Yes? What this should be is this should just be nice sharp spikes at the particular frequencies that I have. As it turns out, that these things that I've measured, and this is some work that I've done over the past year with Chao, who's here, and Emmanuel Gull, who is not, these things are positive semi-definite functions. Why is this? Because they can be written as an inner product on a Hilbert space. And we can make use of this. This data must be a positive semi-definite function. Because of all the noise from the hardware, it is clearly not. So what you can do is you can project it onto the nearest positive semi-definite function. That gets you this. And now this already starts to look better. This peak that previously was negative is now positive. They're much sharper. I still have some other peaks because some noise you can't get rid of, but it's already a much better spectrum at this point just by insisting that I know something about my data and insisting that that must be true. We can do even better. Thanks to a theorem by Cara Theodori, I think, if I have sufficiently dense data, then I can extend this uniquely. And so I can take this data and extend it basically to as long as I want. And this is really nice, because this gets past this I only have limited data problem. Yes, I can now just extend it for as long as I'd like, so that my Fourier transform looks like something appropriate. And now I have two lovely sharp spikes. They are positive like they're supposed to be. I do still have some noise, but I can't get rid of everything. So with this, yes, please.
Your the right green peak is now sharper than
Yes,
anything that you had before. Is
yes.
that an artifact or is that?
Artifact. They're supposed to be the same. It's not perfect, yes, but it's a lot better. I mean, having these peaks be different height is perfectly allowed. Nothing says they have to be the same. Yes.
Can this projection onto the PSD cone be done for very large? Or like, what's the limitation on how much that could be scaled up?
So this is all classical post-processing, yes? So there's nothing of this on the quantum computer. This is just taking my data and like sticking it in a magic box. Okay. So the only question, I guess, is how long can you go in T? Is that the?
I guess I'm picturing, it looks like maybe you have like 50 points here or
Yes.
something. Maybe projecting onto the PSD cone or whatever is efficient there, but
Yes.
once you get up to
Great.
500,
Okay.
is it still?
Doing this is not hard. So you can do this one of two ways. You can compute all the eigenvalues, which sounds hard, but because the matrix structure is tuplets, there's an n-squared algorithm for that. There's also other ways that you can project this where you don't have to compute the eigenvalues. There's a couple efficient ways of doing that from, I don't know, 40 years ago where somebody wrote down how to do this. So these are, I don't know, 2 minutes. They're not hard.
So about like this data,
Mhm.
you have two main keys.
Yes.
Those are clearly signals.
Yes.
The rest, do you think they are signals or like?
I mean, I don't know. They came from this, right? Like out of all the data I showed you, I picked the worst one.
Yeah, but,
Right.
but you also have a like presumably this is not a quantum advantage. You have a classically you know the answer.
Classically, I know the answer. Yep.
Yeah. So are those?
Yeah, I don't know. I mean, you would work a bit harder. I mean, also, so this is just doing.
I mean,
Yeah.
classically, you actually know what
Yes,
this is
yes.
not supposed to be.
No, you would think there's peaks there, and there's not much you can do about it, right? Because that's what's in your data.
Oh, no. Well, what I mean is, we heard on Tuesday there are lots of methods that can be done to, you can call it denoising or
Yes.
signal processing.
Yes.
But one common thing that needs to be assumed is how many peaks.
Correct. Yes.
There are, and
Yes.
The rest must be noise.
Yes.
So given you can do the exact calculation, and
Yes.
so yeah, the rest of the peaks should they be viewed as a data or signal, or should they be viewed as noise?
Well, okay. My model does not respond at these frequencies, so they should be noise.
They're noise.
Those are noise. But if you were to run this calculation, I could not tell you that. Right? I wouldn't know. The only way I could know is if I know, okay, well, this model has this many bands. So sometimes you know in advance how many peaks you have. Yes, within a given frequency range. So I know because, where is it? I know because the band structure looks like this, then in this case, I should only have one frequency ever. And in this case, I should only have two frequencies ever. And this you can do just by electron counting. So some of these things you don't necessarily have to worry about. If you have a whole lot of excitations or a whole lot of like bands within a dense space, then you probably can't do that as much.
Which means that from an input-output perspective, you will be happy if the input is the raw crazy thing, output are just some.
Yeah. Yeah.
And then you can post
Yep.
and do some steady state stuff.
Yeah, exactly. That's what you would do, right? Or what I would do if I were to be given this, I would say, well, let me make a plot at this noise floor and at this noise floor. Or maybe I would try and take this data and smooth it with a Gaussian and then do these things on top of it, right? There's other things other games that you can play. Okay. So the point of this is one, I really like the work that was presented this week with trying to do something with signals processing, and I think we can take that a whole lot further, and we should. Yeah. Okay. Yes.
So if I try to understand this last statement, can you just repeat like exactly where you have the data and where you are extending it? And what is the assumption for this unique extension?
Okay, good. That was like 3 questions. What was the first one?
Where do you have the data and where are you extending
This
it?
is my data.
So that's defined on every point on that wherever it is.
Yes, 1, 2, these are all my points.
Okay.
Yes? And then the next question was?
To what domain do you extend it?
Great. Okay. So if you have continuous data, which I don't, if you do, you can extend it to all of R. You don't have to do anything else. If essentially the reason is your signal contains some number of frequencies, yes? No. It could be an infinite number, yes? But if I have continuous data, then that's enough to reconstruct my entire function.
From that limited.
Yes, if I had continuous data at all possible time points. I don't.
Absolutely zero noise.
Yeah. No. This is just a mathematical statement. Yeah.
Theorem
Yeah.
should be absolutely
Yes.
zero.
Yeah, but zero noise.
You have a little bit of noise.
Oh yeah, no. The moment you have noise, things go wrong. Yes, but like you need to have perfect data, so then you can extend to all of R. Now we don't. Right. So the best you can say is what this does is it takes your signal and it says, okay, well, it has effectively some low rank decomposition in frequency domain. Yes, and this just extends that out, having done some low rank decomposition. But you can extend it to all R. Just you might not get, for example, like this data is not long enough to get a really slow frequency. Yes, so you'll never see that. So you're still, in some sense, limited.
But the idea is that whatever criteria you already have in mind, presumably it's not this.
No, presumably it's not this. But you can, and this, you have to be a bit more careful. What you can say is that there are extensions that you can make based on your data. Now they are not unique, but you can do them. And you can build a positive semi-definite extension.
But maybe if there is some additional assumptions, such as there's only very few peaks.
Sure.
Yes.
You
Sure.
have an extension.
Yes.
Smoothness something.
Yes. Yes. Yeah.
Because usually in PDs and in applied math, you need to do a lot of work. You need to prove unique continuation, that something that it is in a small interval
Yes.
to extend it. And
Yes.
here it is even worse because as we saw, there is a lot of.
Yes. Yeah. No, this statement here, it does not apply to our data. Yes, this is more to motivate, like, why can you do this in the first place? Okay. Okay, good. I have until 12:20?
Yep.
Oh man, okay, all right. So I will try and take 7 minutes and tell you about Lie algebras. We'll see how this goes. All right, why should you care about these in the first place? Well, we saw a little bit of this earlier this week in Christian's talk. If you're building some circuit either for time evolution or for some variational ansatz, one way that you can talk about quantum control or expressibility of these circuits is by computing a thing called the dynamical Lie algebra. Given some set of operators, either this is, for example, for adapt VQE, or I have some operator pool, or in a Hamiltonian, I can produce a thing called the dynamical Lie algebra by essentially taking these operators and calculating their closure on a commutation. So I commute them until I'm blue in the face, and then eventually I will not find any more terms, and then I call myself done. There's a lot of useful things that you can learn from this. We've done a bunch of work in this space. This will be presented, I think, 2-3 weeks. When's the quantum machine learning workshop? 2 weeks. So one of the authors is coming to present this. You asked about circuit compression. That sits here also. The one I want to tell you about in the next 6 minutes is using Cartan decomposition for exact time evolution, because it's kind of the one that everything else sprung from. Okay. So we've heard a whole lot of talks about Trotter, decomposition, and various ways of implementing time evolution. In another corner of the world, people were working on unitary synthesis, essentially doing some kind of decomposition on this dynamical Lie algebra. The top you may not have seen, the bottom you might have. Yeah, this is like the unique, or the SU4 that can capture basically everything you want. If you have any 2-qubit operator, you can always write it in this form given some U1 through U4 or V1 through V4. And this is optimal. You cannot do any better, except in some cases you can do 2. So this you may have seen. Okay, so what we're going to do is I'm going to talk you through how do you take these ideas and how do you apply them to time evolution. So here's our task. our task is the exact simulation of a time-independent Hamiltonian. So to fix your brain, or to fix your, not to fix your brain, to fix your mind on an idea, so here's one example of a Hamiltonian. And usually what one does is you break this into tiny steps so that this is approximately true. And then you string these together in some circuit. And in this case, it's nice and easy. But if I have longer Paulis, then I can use these Pauli gadgets to like implement whatever exponential of a single Pauli that I want. So this is Trotter. This is not what we're going to do. You could also do the following. You could show that I can write the exponential of an operator as a product of exponentials of single Paulis in the SU2 to the n algebra. This can be done. It doesn't work for the entirety of SU2 group at the same to the n of group at the same time, but it works for the small patch that you care about. So first, an observation. This is too many terms. Why? Because my Hamiltonian, right, if I think about this from like a Magnus expansion, does not generate all of SU2 to the n, right? It generates whatever you get under commutation. So really, we should replace this by the dynamical Lie algebra. And so if I think of this as sort of like a space, right, I've got all of SU2 to the n, I've got my Hamiltonian that lives in there, and I've got something, we call it G of H, but it's the dynamical Lie algebra that in principle is smaller. How much? This depends on the model. Full SU2 to the n scales like 4 to the n, right there. Heisenberg has a dynamical Lie algebra that scales also exponentially. These two, or three, these are the models that are free fermionic-ish. They only have a quadratic dependence on the number of qubits, and so these can be simulated much, much, much more efficiently. And this is because, well, they're simple, right? They're free fermions. We know what to do with these things.
What do you mean by ish?
Which ish?
The free fermion-ish?
Well, okay. These are, you can turn this via a variety of transformations into free fermion models. Thank you. So this is the first observation. The second, this is the dimension of the dynamical Lie algebra. Log. Just how many terms did I generate? This is why Heisenberg is hard, because I generate almost all of SU2 to the n, right? I generate just an insane amount of terms. Okay, so
And the scaling for the galaxy model is
it's like nn minus 1 over 2 or something like that. Yeah, it's n squared. So these are quadratic. Okay, so this is one observation. The second thing is the following. Don't read all of it. I'm going to talk you through it. You can build a thing called a Cartan decomposition, which takes my large algebra and splits it into two pieces. One called K. That's a K. It doesn't look like it. That's an M. It splits it into K and M. It's not unique. There's a variety of ways you can do this, but you can do this. And then within M, there's a special thing called the Cartan subalgebra that if you've ever taken a Lie algebra course, you might have heard these words. Why is this useful? Well, because via something called the KAK decomposition, what you can show is that you can exponentiate any operator you like in this way. Exponentiate elements of K, exponentiate elements of H, exponentiate elements of K. And the important part is that T only goes in here as a parameter. These things do not depend on it. H is abelian, so this is really, really easy to do. This is hard work, but this stuff is easy. So in other words, if you do this once, you now get a circuit that you can use for any time that you like. Okay, yes?
Are these like, let's say, readily available, like for this Ising model, for example? I mean, these algebras, or is this?
Yes. We also have code that will calculate them for you. They're basis dependent, right? So depending on what they look like, you get different. Yeah. Okay. So that's the second thing. We can now simplify this further in this way. The final thing we have to do is I now still have these angles to find. So I don't have the time to talk about it in detail, but I will tell you sort of the main idea. There is a relatively simple cost function to calculate. It doesn't look simple, but it is. And you only want a local minimum. This is one of the really nice things. You can optimize this entirely by finding a local minimum of this cost function. So it's actually really, really cheap to do compared to finding a global minimum. I'm happy to talk more in detail afterwards, but people also want to eat, presumably. Yeah.
Yeah, okay. Let's talk afterwards.
Okay. So yeah, this is what you do. You generate the dynamical Lie algebra, you find a Cartan decomposition, you find parameters, you build your circuit, and then simulate for any time that you want. It may be a really, really deep circuit. Yes? The number of terms here is roughly the number of terms in your dynamical Lie algebra. So there may be an exponential number of them depending on what model you want to simulate. That's the one downside.
Also, is finding the, I mean, I imagine finding the Cartan decomposition is not efficient.
That's fine.
Heisenberg.
That's easy. Finding a split into K and M is very easy.
Like coming up with the K there that's in the circuit. That, like, is that
That's not hard.
okay?
I mean, you take your
I just don't
you
understand.
build your dynamical Lie algebra and then you split them into two by a rule that you design. Yes,
But building the Lie algebra is probably very hard, right?
that could take time. Yes,
Like it's almost exponential.
yes, that could take time.
So is finding the capital K computationally hard, so to say?
You have to find these angles. You have to optimize this function. We have some improved ways of doing it. It does take time, but you only have to do it once, right? And in principle,
Yeah, it's also exact, right?
it's exact.
Yeah.
So in principle, one could take this, do this for a whole bunch of models once, yeah, publish these parameters, and then you have exact time evolution for this model for however long you like.
So for small t, maybe better just order it.
Yep.
But for larger t, there's
Yes. Yes. There will be a point. So you don't want to do this for short times, yeah, because you would just do Trotter. But if you want to do this for all times, then yes. The other nice thing about this is that your circuit structure is always the same for all time, which means the noise characteristics of your machine are always the same. You don't get more noisy the deeper you go. And this is helpful for signals processing.
Can you give us a sense for how expensive it would be to do this for like the Heisenberg model? Like, is it exponential in the number of sites?
Yes. Yeah.
Yeah.
Yeah. Yeah. No, it has to be.
So is your idea to like do this for smaller systems, and then that could help improve Trotter steps?
Good. So you could, for example, do this in the sense that Christian talked about, where you built this for some small light cone, right? That's one way you can do this. We have actually, yes, this is probably the best idea. You don't want to do this for 100 sites, yeah? Or you can use this to build things on top of, right? Because not all those parameters are important. Clearly not. So there are ways that you can get around some of that, but this is a point to start from. I just sort of wanted to show you what some of this data looks like. That's the data. Again, doesn't look great, but the same argument applies. You can take this, do a bunch of signals processing on it, and do some DMFT, condensed matter-y things that are otherwise sort of hard to do. Yeah. Okay.
The first line there, is that saying that the depth of the circuit is n squared?
For these models, yes. Yep. Okay. So that's this one. The one I did not talk about, but I am happy to tell anybody about is how you compress things that also belong to these. You can do time-dependent Hamiltonians with that. So I'm happy to tell you about that whenever you like. We have code for both of these. You're welcome to use them and check them out. Okay. There's my propaganda slide. I'm going to stop talking and take any questions if you'd like.
And this slides on, it talks online also.